Welcome to Lesson 5-4, Newton's Law of Universal Gravitation. The objective here is really just to be able to recognize Newton's Law of Universal Gravitation and when to use it. So, legend says that Newton came up with the idea of universal gravitation when he saw that an apple was falling straight down from a tree. He noticed that the apple actually accelerates from rest down all the way until it hits the ground, and he realized that there was something missing in our understanding of the cosmos based off of this, because before his time, it was understood and thought that any force being applied must be applied by contact between two objects. Okay? But that kind of throws a wrench into the idea that an apple accelerates downward with nothing touching it. So Newton was thinking, is the force that causes this apple to accelerate downward the same centripetal force that causes the moon to maintain its circular orbit around Earth? All right, by now we understand that in order for an object to maintain circular motion, there must be some constant centripetal force. And Newton thought that that centripetal force came from gravity. That said, he considered the fact that gravity always points toward Earth, okay? And then he was applying that to the idea that that same gravity is pointing toward Earth from the moon, all right? So even though the moon is so far from the Earth, he still was able to figure out that the relationship between force of gravity is the inverse square of the distance from the center of the Earth. Now, this had to do with a lot of calculus and everything like that, but we know that the moon is 60 times farther away from the center of Earth than we are on the Earth's surface. That said, that must give us a relationship such that the moon's gravitational, the force that the moon experiences from Earth's gravitational pull must be 1 over 3600. But the thing is that the moon itself has so much mass that it also contributes to the force of gravity that the moon experiences from the Earth. That said, Newton said that the force due to gravity must be proportional to the inverse square of the distance between two objects, but also must be directly proportional to the mass of the two objects that are being pulled together by gravity. That said, he suggested that the force due to gravity must be proportional to the two masses that are being pulled together over the square of the distance between those two objects. Of course, when we take the units of this expression and the units of force, we're missing something. So Newton said there must be some universal constant to suggest that these values give us some gravitational force. But he didn't just get there in one step. He considered that the force that's causing the moon to stay in orbit around the sun must be centripetal. He then followed by saying, well, the force that's causing planets to stay in orbit around the sun is also centripetal, and it tends to have the same relationship, the inverse square of their distance, as the moon has with Earth. That said, he posited that maybe that's the exact same thing that's causing our entire solar system, our entire solar system to revolve around the center of the Milky Way galaxy. Okay, all of these values mathematically should check out to having an inverse square relationship with distance between the two objects. But Newton wasn't on his own able to find out what constant we could multiply this relationship by to give us the actual force. About 100 years later, a scientist by the name of Henry Cavendish put together some experiment that allowed us to actually calculate big G, all right? And by really finely tuned instruments that had two masses very close together, he was able to measure the force and the time that it took to bring those two objects together on a nearly frictionless swivel. It was a very interesting experiment, but what he was able to find out is that that big G that you see in Newton's gravitational law, universal gravitational law, is equal to 6.67 times 10 to the negative 11. All right, and you're wondering what units does this constant have? Whatever units we need in order to make this relationship have newtons. So what that left us over with is just meters cubed over kilograms second squared. Kilograms times second squared. So, that said, we were finally able to use Newton's law of universal gravitation to find the mass of the Earth, and not just find the mass of the Earth, but also find the gravity at the surface of any planet that we know the density of. That said, you know how that on the surface of the Earth we usually use mg as our force due to gravity, mg. But if we take that mg and we set it to Newton's law of universal gravitation, then what we can do is we can solve for g in a way that allows us to plug in the mass and radius of any planet to find the acceleration due to gravity on the surface of that planet. It's a beautiful equation. Here's a couple of constants that you might want to keep in mind. Earth's mass and the gravity at its surface, as well as the moon's mass and the gravity at its surface. Take note of these values. And also you might want to take note of the distance between the Earth and the moon. This will be helpful in some of the practice problems that we're doing. All right. Good luck, and I'll see you in the next one.